Right.
Ali, you're now
hi,
on
everybody.
speaker.
Okay. Hi, everybody. My name is Ali Shirsavar from Biricha Digital. Thank you very much for joining in. And over the next hour or so, we are going to talk about why PID controllers are not suitable for stabilizing many of switch mode power supplies. We're not saying that it's impossible. We're just saying there are better ones out there. This has become a bit of an emotive subject with regard to PID. People are very attached to PID, and when we suggest that perhaps there are better ones, people get upset. So it's only our opinion. If you wish to carry on using PID, that is entirely up to you. It's just we're going to highlight some of the shortcomings of PID, after which you can decide for yourself whether or not you wish to use it. Let's have a look about PID controller and a switch mode power supply. PID controller, why do we like PID controllers? PID controllers are extremely easy to design and implement. With less than 10 minutes on any search engine, you find many analog and digital realizations. There are even automatic tuning algorithms will try to tune the KP, KI, and KD you'll gain very quickly and very easily. Now, whilst the controller and its close relative PI, proportional integral, are excellent for stabilizing things like motor control systems or temperature controllers and things like that, in our opinion, they are unsuitable for compensating most switch mode power supplies. And furthermore, although one may be able to get away with a PID controller in a current mode converter, or for example, if you've got a lot of ceramic capacitors and no electrolytic capacitors, there are better alternatives. So if you are intending to use PID, then I highly recommend that you read the excellent text by Christoph Basso, which he presented in APEC 2011. It is available for free from Mr. Basso's website. And he does show how to do a PID nicely in order to stabilize the system. But the notion that you can just mess around with KP, KI, and KD and get a power supply stable is something that we're going to hopefully explain why you can't. The main attraction of the PID is that one does not need to know much about control theory. Frequency response analysis, pole zero placement, phase margin, gain margin, the stability criteria. The beauty of PID in many applications, such as motor control, is that you don't need to know about any of these. You get free gains, and you heuristically change them, and that is a posh word for semi-educated trial and error. So you usually increase KP until the thing starts oscillating, then you reduce KP a little bit, then you increase KI until the steady state error goes away, and then you increase KD a little bit to give it some damping, and then you increase KP a little bit more, and then it's tuned. So this is done without the need of knowing the transfer function or the frequency response and so on, and that is why it's attractive and it's such a fantastic and versatile controller. The problem is that with power supplies, it is not the best option. So although it's extremely effective in millions of applications, for power supplies it's probably not the best thing. And here's the reason why. PID's transfer function, as we'll show you in a minute, has got only 2 poles and 1 pole on origin. Now, most experts for designing power supplies, switch mode power supplies, agree that it should be designed in frequency domain and not in time domain. And yet PID is a tool whose main advantage is that you don't design in frequency domain, you design in time domain. So there is a contradiction here. If we are using PID's main advantage, which is just adjusting free gains, then we are working in time domain. But everybody says we should design a power supply in frequency domain, and for good reason, because if you design in frequency domain, you have a lot more information about the stability. So you can see from the onset that PID is not going to be that suitable for power supply. The transfer function of the PID compensator looks something like this, where you have H of S, your transfer function, is equal to KP, that is your proportional gain, plus KI over S. KI is your integral gain, 1 over S is your integrator, and KDS is your differential gain, with S being the differentiator. Now, if we take common denominators, this equation becomes that. These two are mathematically identical. All we have done is we've taken common denominators. Now, you can immediately see that the numerator is a simple quadratic equation. It's a polynomial second order. That means that you have got two zeros, and in the denominator, you only have one pole at origin. So what I'm saying is that you've got two zeros here because it's a second order polynomial. It's just one quadratic, and you've got one pole at origin. Please note that for a realizable system, you cannot have more zeros than poles. So in real life, you also have an extra pole here, which is usually either the bandwidth of the op-amp that you're using, or you actually place it, but you place it very high so that it does not impact the controller. If you put the pole low, then it's not a PID anymore. It's PID plus an extra pole. So to make it PID, you need to shift that extra pole to make it realizable, which is here, a bracket here, right, for a real system, very, very high, or you just rely on the bandwidth of whatever it is that you use. Now, the transfer function, to find the zeros, we had a quadratic equation. We've seen this equation from school-level mathematics. It's minus b plus or minus b squared minus 4ac over 2a, where in our case, a is kd, B is KP, and C is KI. So if I substitute that in this, I end up with the transfer function of my PID controller, and you can easily see that I've got two zeros. I've got a 0 over here, S plus something, and I've got another 0 here, S minus something. And I have got S over here, which is my pole at origin. Looking at the equation above, you'll see that the positions of both zeros and the pole at origin are interdependent on all three gains. If you look here, you've got KP, KP, KD, KI, KI. If you want to take a constant out of these two brackets to have K over here, if you do that, you'll see that this pole at origin is also interdependent on these three gains. So if you actually change any of the gains, you mess up in frequency domain the position of everything. So if you've got KP, KI, and KD, which is the whole attraction of PID, and you say, oh, I'm going to increase my proportional gain, the position of this will change and the position of that will change. If you change KI, KD, anything will shift the positions of the poles and zeros. So conclusion, you cannot design in frequency domain by just adjusting KP, KI, and KD because they're interdependent. There is no easy way out, and you have to deal with poles and zeros. If you're going to derive the poles and zeros like we have done over here and try to factorize them and try to solve them simultaneously to work out which KP, KI, and KD you need to place a pole or a zero at a certain location, then you might as well use a type 2 or a type 3. So the whole point of a PID is that it dispenses with frequency domain design. And yet, we are saying, okay, well, if we're going to design a frequency domain, we're going to have to do all this extra analysis in order to do it. So why will our PID not work very well in stabilizing power supplies? We're going to show you a demo in a minute with WDS, and we're going to show you what will happen if you actually use a PID. Here's the problem. Now, from the stability criteria, we know that the crossover frequency should be at least 1/6 of the switching frequency. I usually actually go for 1/10 or even 1/20. So I try to cross as low as I can, depending on the specification. We know that the phase margin must be bigger than 45 degrees. And we know that the gain margin must be better than 10 dB. And you also want to shallow down the slope as you cross. So that is the 3 or 4 criteria that you need to meet in order to make a stable power supply. Now, from the following figure, you can see that WDS, this is an automated design software that we have, has designed a nice voltage mode compensator. It's a type 3 compensator for a voltage mode power supply. And you can see that you've got a switching frequency of 200 kilohertz, crossover frequency of 20 kilohertz, phase margin of 60 degrees, and 27 dB of gain margin. This is a nice power supply in terms of the stability. Now, here are the danger zone. You really should not cross before this resonant bump, because that would make the system conditionally stable, conditional to the height of this bump. If you start crossing around here, so 0 dBx is around here, and for whatever reason the damping of your system changes and the height of this bump changes, you may end up with this bump crossing the 0 dB axis. So ideally, although it's possible, you don't want to be crossing in this region in a voltage mode power supply. Then you obviously don't want to be crossing on the resonant bump, because that's going to be shifting up and down. So that is a danger zone that you want to avoid. Then the area straight after the resonant bump is going down at 40 dB per decade. Yeah? And even if you try to cancel this, straight after will still be going at 40 dB per decade. So you don't want to be crossing around there either, around here either. And ideally, you don't want to be crossing around the ESR 0, because the ESR 0 changes with temperature, with aging, and so on. So really, you're quite limited as to where you can cross. You ideally want to be crossing somewhere around here, or you want to be crossing somewhere around here, okay? So for good performance, the region that we can cross must be very judiciously selected as to where you can actually cross, and then the phase and gain margin is adjusted. And you cannot do that by just messing around with KP, KI, and KD. It does not give you enough information to say, well, you know what, I actually want to cross at 5 kilohertz, because you don't have that information with the PID. You just have KP, KI, and KD in time domain. So from the previous power supply that we designed, we then ran a simulation. And this is a transient response that we got. That is with a type 3 compensator. You get a beautiful transient response. You recover in less than 100 microseconds, and there is no ringing. And if you zoom into this area, you'll see that you've got perfect triangular voltage ripple on the output, which is due to the ESR of the capacitor. Okay? This is a simulation, by the way, from WDS. So why will our PID not work very well? Let us not try to stabilize the same power supply with a PID. Let us give ourselves an unfair and unrealistic advantage of using WDS, the software, and design it in frequency domain instead of time domain. Now, in real life, you will have to do masses of mathematics in order to design in frequency domain. But we're going to just show even in frequency domain, it's difficult to design with PIDs. By the way, if you want to try this for yourself, you can just download the software, the design software that I'm showing you from this link, and you type in the free version is limited in that we have locked the voltages, input voltage, and output current, but you've got full access to all the other features. And the demos that I'm going to do here is going to be with the demo version of the software, so you are not going to be limited at all in trying these yourself. So if you'd like to try and see whether you can stabilize a power supply with a PID or with a Type 3, just please download the software and have a play. So we know that with PID, we have 2 zeros and 1 pole at origin. For simplicity, instead of having that massive equation, let's just represent it like this. I've got a constant, which I've pulled out of the brackets, and then I have got S plus 0,1 and S plus 0,2. So I've got 2 zeros, and I've got a constant, and that's my pole at origin. 1 pole at origin and 2 zeros. Okay? We also know that for a voltage mode power converter, our plant typically has a low/DC gain. That's due to the action of the PWM, the gain of the PWM block. I've got a double pole at a resonant frequency of 1 over 2 pi square root of LC, and an ESR 0 at 1 over 2 pi ESR C, where ESR is the equivalent series resistance of the capacitor, output cap, C is the output cap, and L is the choke, the output choke. It will show in the next slide how this is all going to be done. Now, let us see what we can do with just 2 zeros and 1 pole, which is what you have in a PID. Okay? So, voltage mode power supply performance with a PID. So now let us see that how you can compensate this in WDS. In order to do this, note that WDS does not design a PID compensator. We just haven't bothered putting it in. Yeah. However, you can convert a type 3 compensator into a PID by placing two of the poles very, very, very high. I will show you that in just a minute as I run the software. So if you stick two poles of a type 3 compensator at, let's say, 100 megahertz, they go out of the picture, and then you end up with two zeros and one pole at origin, which is this. So you create yourself a PID compensator with a PID. Okay, so in order to meet the stability criteria, we must place our two zeros around the resonant frequency. Otherwise, we cross with a sharp slope, and we can have a pole at origin, and we can shift that pole left or right in order to cross at the right place. Okay. Now, if we cancel the two plants pole with two PID zeros and then place our pole at origin, the gain of our open loop frequency response will be rolling off at a rate of 20 dB per decade. Because if you look at this, you're going down at 20 dB per decade here. Then you hit two poles. So it's two poles plus 20 dB. This is the pole at origin, yeah, for the PID. And you've got two plant poles. So if you put two of the zeros here, you cancel the two poles and you continue going down at 20 dB per decade. The problem is that then you hit the ESR 0 and the thing is going to go flat. And we're just going to show you that in a minute. So if we cancel the two plant poles with the two PID zeros and place our pole at origin, our open loop gain, as you saw from the previous diagram, will be rolling off at a rate of 20 dB per decade. We will then hit the ESR 0. Now, unless you've got ceramics, which means that the ESR 0 is very, very high, if you've got electrolytics, you hit the ESR 0. Our gain is going down at a rate of 20 dB per decade, and then we hit the 0. Then the gain plot will go flat with a gradient of 0 dB per decade. So we'll stop moving. It'll start flatlining, like so. Now, there are two alternatives. Either it will go flat before you cross over, or it will go flat after you cross over. And we're going to look at each one of these. Neither option is really desirable that you can do in order to ship a power supply. The best way to do this is by doing a demo. I will show you that. First, please have a look at the diagram. Here is one that I designed using WDS and a PID compensator, and this is a 0 dB line. So I'm showing that it is going flat before it is crossed over. And these are the values that I used. I placed the type 3 compensators poles very, very, very high to get rid of them. I placed the two zeros around the resonant frequency, and I then actually kept the pole at origin so that it actually stays before crossing. We will do the other one in a minute. So I'm going to run WDS now. Okay, so I'm running WDS right now. Now, this is the evaluation version, so these are exactly what you will get when you download it. So it's no different to what you download, and you can try this for yourself. First, let's look at the loop, and you will see that it has designed a power supply with a crossover frequency of 20 kilohertz, phase margin of 60 degrees, gain margin of 27 dBs, and a slow path crossover frequency of minus 22 dBs per decade. That's all well and good. That is with a type 3. Now let's go and change to type 3 to a PID and see what happens. We don't need to check any of these. The only one thing that you should look at, WDS has designed the power stage. Output choke is taken about 250 microhenries, and the output cap is taken at 35 microfarads. And these to give you a resonant bump around this area, which is around 1,700. Yeah. Okay, and the ESR 0 should be displayed, and there we go. It's at 11 kilohertz. So we're going to convert this into a PID now. I go to controller design. This is a type 3 compensator. The only difference between a PID and this type 3 is that these two poles in a PID do not exist. So I can shift these up and get it out of my system. Okay? So I put manual pole placement, and then let's see what happens. I'm going to put the poles very, very high. And then I'm going to put the other pole also very, very high. Now I have a PID, because these two are not in the picture. And then I'm going to put the zeros around this resonant bump here in order to cancel them. So that's 1,700. You can see as I change that, it immediately changes the Bode plot. There we go. So with a pole at origin of, at the moment, 1,200, 1,700, 1,700 as my two zeros, you can see that on the Bode plot, I don't actually cross. I haven't crossed. Now, the stability criteria is only valid if you cross. What is your phase margin if you don't cross? What is your gain margin if you don't cross? Bode's analysis only was based about the loop crossing. Now, if you don't cross, none of these terms actually mean anything. So you have zero information about the stability. If you really want to know the stability, you need to do a Nyquist plot, which Bode 100 does for you. So you can have a look at it on Nyquist plots, and then you can see how close you come into the -1 point. It's not crossing. One other thing that you can do is to actually simulate. So it has designed the circuit. It is giving you all of the capacitance and resistance you need. This is now the circuit of the buck converter, and WDS has calculated all of these values. So we create a net list in LT-Spice, and you just run on close. You can do open loop, closed loop, or frequency response. Let's do a closed loop response on this, and you run the simulation. This will open LT-Spice for you. And it's running the simulation. It will take some time, so I have actually done the simulation in advance, and I've put it in the presentation. So let me just put that back on. Something just went bleep in my ear. Is there, okay. Is everything all right? Not Florian, is everything all right? Okay. Now then, so this is what we designed with PID. Oh, yes. This is what we designed with a PID, and you saw that it did not cross. This is exactly what I just did live for you, and this is now the output ripple. Now have a look at this, right? We're switching at 200 kilohertz, so from there to there is 5 microseconds. This is your switching ripple. When you use the type 3, this was a beautiful triangle, yeah? And now you have got this beautiful triangle, and you have got this extra ripple on top of it, yeah? The frequency of this ripple is high, and you can also see that you've got this low frequency modulation going on. So you no longer have a nice flat triangular wave as you expect to see in a power supply. On top of it, you have got a very high frequency. It's about 5 megahertz here, which is going to if it really does happen in a real light system, it's really going to hurt you in the EMC test chamber, because that's going to be a big spike on your EMC test results at whatever frequency of that is, which I think is around 5 megahertz. Okay, so then that was the case when the loop did not cross. And say, well, okay, let's force the loop to cross. Let's reduce the gain. I'm going to move this window because there's a webcam which is right in front of me. So I'm just going to move it to the other screen if you don't mind. Now what I have is a crossover frequency of 20 kilohertz. a phase margin of 142 degrees. A phase margin of 142 degrees. In real life, that obviously will not happen. This is simulation. You have got this massive gain going, the massive increase in phase because of these two zeros, and because this is flatlined and it's going up. In a real life, you hit some bandwidth limitation and this will fall down. And as this will fall down, at some point it will cross the minus 180 degrees, and then you have very poor gain margin, as you'll see. So if I go back here again, so what happens if we do cross? Well, do we get a better performance? The answer is no, we don't. In the following figure, we have changed the position of the pole at origin in WDS to 180 hertz to make sure that we actually cross at 20 kilohertz. 20 kilohertz was the one that we designed with the Type 3, and it gave us beautiful performance. So if I want to do a PID and I want to get good performance, let's design one which has got the same type of crossover frequency, but please look at the gain now. We're crossing, but this is the 0 dB axis here. Look how much below 0 dB axis, minus 2 dBs below the 0 dB axis. So what happens in a real system whereby things shift up and down with input voltage, output voltage, temperature, current, all that? You could be crossing up or down here at any point. Oops. Okay. So this really is not something that you can ship and sell. You cannot possibly, I would not advise you to have a power supply that has got this body plot and you're this close to 0 dBs and ship the power supply. Although this may work in a simulation, in real life, the loop may cross the 0 dB point many times. Also, as I said earlier, this gain is not going to infinitely, this phase is not going to infinitely rise. It's going to hit some bandwidth limitation and it's going to roll off. And it's going to roll off and it's going to hit minus 180 degrees, and then you end up with 2 or 3 dBs of gain margin. Okay? So again, I can do the same in WDS. This is the simulation of this system, and here's the transient response. So the green trace is the Type 3 with 10 kilohertz. You can see how beautiful it is, and this is the transient response with the PID. Even though it got exactly the same crossover frequency, you can see that it's much slower because the phase margin was massive. That's the only way you can do it. Well, actually, that's not the only way you can do it. Without enormous amounts of analysis, you can do a lot more analysis and try and get better. But because of that ESR 0, you're going to have very poor performance. And then, if I put a magnifying glass on here, you'll see that on top of the switching ripple, which is 5 microseconds, it's my switching frequency of 200 kilohertz, you've got 5.8 megahertz ripple on top of that, and that is really going to hurt if you go to a test chamber. So I'm going to go back to WDS now, and now I am going to change my. Let's look at the frequency response. Now it's same as specification. I go back to controller tab, and I keep the poles the same, but I change that. I lower that in order to get it to cross. At the moment, the 0 dB axis is where my mouse is, and I need to push this down so that it actually crosses. So if I change that to 180, you will see that I am crossing around 20 kilohertz. I've got a gain margin of 2 dB. Well, actually, that is not a statistic gain margin because this does not cross, but you can see that it's very low. It's very close to that 0 dB axis if I want to have a high crossover frequency. If I don't want to have a high crossover frequency, I can try to reduce the crossover frequency, but hang on a minute, I can't cross here because now the slope is at minus 48 dBs per decade. This will violate the stability criteria. If I reduce it even more, I am now on the bump. I cannot do that on the bump. If I reduce it even more, I am now crossing still around here, it's just not going to happen. Oh, sorry. Let's go there. I am now crossing before the bump, and that makes it conditionally stable. So there is no good way of doing it with just 2 zeros and 1 pole, and that's why we say that PID is not a good choice. So this was how quickly we managed to just show you by changing the pole at origin that it is undesirable to be crossing at any of these points before you actually design the thing. You can see the crossover frequency, you can see the gain margin, you can see how it's going to behave. Okay, so let's go back to the presentation. Oh, by the way, as I said, the simulation should be finished by now, so I can now show you. If I put a voltage probe on the output of my buck converter, there you go. This is a simulation of the output ripple with the PID that we designed earlier that did not cross. And you can see that you've got a very high frequency ripple. This is actually supposed to be the output ripple here, which is going at 200 kilohertz, right? And on top of it, you've got this high frequency stuff happening. And if you look at the bottom of it, you'll see that they're not flat. It's moving up and down, yeah? Okay, so let's kill that off. Let's close that. So that was for voltage mode. With current mode, it is possible to stabilize power supplies with the PID and current mode. It's certainly possible, especially if you use ceramics. It's possible as well. After all, at low frequencies, the plant transfer function looks like a first-order system. I'm not saying it is a first-order system before the people shout. We all know about the double approximation of double complex conjugate pole at half the switching frequency, but at least at low frequency, it looks like a first-order system, and we usually use a type 2 compensator. So a difference between a type 2 and a PID is that you only have 1 0, 1 pole at origin, and 1 extra pole. So a PID had 2 zeros, 1 pole at origin. A type 2 has got 1 0, 1 pole, and a pole at origin. Okay, so PID has only 1 less pole than a type 2, but we've got 2 zeros. Type 2's extra pole is usually used to cancel the ESR 0. So with this pole missing, again, our loop will go flat at some point. However, if we derive the mathematical relationship between Kp, Ki, and Kd, and our poles and zeros, and then we did clever pole zero placement, just like we did with WDS, we could possibly get a relatively stable power supply. The question is, if you need to do all this analysis and all this derivation, then why not just use a type 2? You have got the transfer function already. There are fantastic application notes and books and everything that tells you how to use a type 2. One excellent book that I personally like, which discusses compensator design in a really eloquent and easy way, is the book by Mr. Sanjay Maniktala. That is Switching Power Supplies A to Z. And that's got a beautiful chapter on how you design a type 2 compensator, and it's done the analysis for you. The work is there. You don't have to go through and analyze all the PID stuff in frequency domain in order to do it. And then finally, if we talk about PID and digital controllers. Now, the PID has been suggested by almost all digital power supply IC vendors. There's a little bit of an irony here in that actually a digital power supply is by far more susceptible to instability when used PID and analog ones. And yet, you know, all major vendors are got tools for PID compensation. The reason is that the phase in a digital power supply deteriorates much faster than the analog equivalent. Now, if you consider the previous slide that I was showing, the phase was shifting up. Although in real life that will not happen, we did not get the phase to hit minus 180 degrees, so we did not have a gain margin issue. However, with the loop flattening and the gain margin being sorry, the gain being just below 0 in digital, because the phase does deteriorate and fall down, and it will cross the minus 180 degree point, you actually may end up with just 2 dBs of gain margin. You'll see that in a minute. Again, in the next figure, I've used WDF to design a digital power supply with, again, similar specification. And again, you can try this yourselves. This is the digital one, okay? Now, look at the phase loss here. So this is due to the sampling and reconstruction in a digital system, and it's due to the fact that you've got some calculation delay and things like that. But it has got big implications because it is now crossing 180 degrees, minus 180 degree point, which means that your gain margin is going to be really, really poor. Please note that I've had to change these because SPICE would not converge. This was so close to 0 that I could not get LT SPICE or any SPICE engine to converge because it was literally near instability. So I have messed around with these poles and zeros a little bit to show you what happens, but also can do the simulation and then run and show you the transient response. So if I go back to my WDS, here is an analog system. WDS designs digital systems as well. So all I do is select digital control. Now, watch this phase as I go from analog to digital. There you go. Analog, digital. And you can see immediately in digital that you are going to hit minus 180 degrees. And your gain margin here now is 0 dBs, because at the moment, you are literally on the 0 dB line. This is not good. So let's go back to my controller design and let's change some stuff and see whether we can make it cross and go down. So if I reduce these poles, I'm actually cheating because I don't have a pole. This is a PID controller. These poles do not exist. There you go. Now I'm crossing better. My gain margin is 3 dBs, yeah? And believe it or not, WDS actually does simulate in SPICE a digital control as well. So then I run the simulation. I don't know if it'll converge or not because it is so close to instability. So this is the way we have simulated a digital system in SPICE. There are papers that teaches you, that tell you how you do zero order holes within SPICE. So we've used zero order holes. So this is a proper digital compensator in SPICE. The power stage is exactly the same. It will take longer to run, obviously, because now we've got all these zero order holes, which is effectively emulating the digital compensator. But the results will be very close to the real digital system, purely because it's actually digital. It makes life, in calculation terms, makes life a lot easier. Okay, so this is running. It's going to take a while. So what I have done is I have actually plotted, oops. I've actually plotted the results for you. Here's the transient response. This is after a 50% loader step. Please note that I have got 72 degrees of phase margin. I've got 72 degrees of phase margin, but this ringing, this massive 1.5 volt drop in voltage is with 72 degrees of phase margin. The reason is that I've got 2 dBs of gain margin because I'm using a PID, and I have cheated anyway because I have reduced these poles that I don't have in a PID in order to give myself a better crossover, a better gain margin. Okay, so although we have 72 degrees of phase margin, the out drops by around 1.5 volts, and it rings. The reason is that gain margin is very poor, and this is only a simulation. Please, and in real life, I will be very confident that in real life this thing will actually be completely unstable. Please note, as I showed you, that WDF actually does simulate a digital power supply. So again, you can do this yourself, but be aware that you may have convergence issues, not because it's a digital controller, because the gain margin is so close to its stability, and SPICE understandably struggles. So the conclusion then is that PID controllers are excellent for thousands and thousands and thousands of applications. It's just that power supplies is not one of them. We would not recommend using it. By all means, if you still would like to use PID, by all means do so. The debate has been going too long. We just feel that there are better alternatives, and that would be Type 2 and Type 3 compensators. As you know, we run quite a lot of workshops on power supply design. The next one in analog power supply design in Garching next week. Actually, I'll be in Germany. That is actually sold out, but there will be one in California in the March period. The weather will be beautiful, so if you can get expenses to go to California, I highly recommend that one. Or if you're watching from the US, oh no, that'll be the evening show. And then we've got a digital power supply design workshop that is still seats available. There is going to be between 1st of December to 3rd of December, again in Garching near Munich. Please register soon because that one is selling out fast. And then we will run it again in the US in Q4 of 2016. We have a digital power supply design with microchip. The other one was with TI, and the dates need to be fixed, but there is going to be one in April in Munich and one in May in Boston. And finally, we've got analog and digital PFC design workshop with TI, and we're not going to run that in Europe at the moment, but we will run in Q4 of 2016 in Houston. So all that remains for me is to say thank you very much for listening. I hope you found it informative, and I now I yield the floor to Florian, who is going to take over. Thank you very much, everyone.